I'm extremely happy to participate in the annual meeting of the Indian Academy of Sciences, and also to deliver this special lecture on weather and climate prediction. First of all, thank you, Dr. Partha and Indian Academy, for giving me an opportunity to give this special talk. And next few minutes, next 40 minutes or so, I'll be talking about recent advances in weather and climate prediction. As all of you know that weather and climate predictions are very useful for many users as well as sectors. It has a huge socio-economic impact. First of all, by giving predictions, we help for disaster management, especially from tropical cyclones, floods, heat wave, etc. Our forecasts are also given to agriculture, especially for farmers and fishermen. Public weather forecasts for general public. Aviation industry. Aviation, for example, when we fly in the airports, when takeoff as well as landing, as well as while flying, pilots need information about weather as well as forecast. And water resources management, especially how we manage reservoirs. And new industries have come up with a lot of requirements for weather and climate prediction is energy and power sector. And I'll give a few examples how we give forecast for energy and power sectors. Then, of course, there are many sectors where weather and climate predictions are useful. For example, health sector, tourism, pilgrimage, transport, etc. So there are many. And classification of prediction, we predict in different time scales, starting from nowcast. Nowcast means nothing but you tell event which is going to happen next few hours, maybe 3 hours, 4 hours. A short-range forecast, which is very common, which is very known to our general public, is we give a forecast for next 3 days what will happen, whether heavy rainfall can occur, or whether heat wave can start, whether cold wave can start, whether a thunderstorm can happen. This kind of forecast we call as a short-range forecast for next 3 days. Then medium range, next beyond 3 days, 4 to 10 days, we call it the medium range forecast. And extended range forecast, 11 to 30 days forecast. So that's up to 1 month, we call it extended range forecast. And seasonal, also monsoon seasonal forecasts are very popular in this country. It's up to 1 season. Then also we have decadal, some people do decadal predictions. Then of course climate change predictions. So we do everything, all these things, except we don't do much work on decadal, but I would like to inform you that some research activity we have started now to make a decadal prediction system in this country. And why we give different ranges is depending upon the weather system and also depending upon the requirement, these forecasts are given in different range. So this is the same information which I put it in a pictorial form. Is the forecast starts from minutes, hours, days, 1 week, 2 weeks, months, seasons, up to decades to centuries. And the left-hand side, you can say that it starts from warnings and alert coordination, then watches, then forecast, the threats and assessment we can make, then guidance, outlook. Then last, climate change we call scenarios or projections we call. If we talk about next 50 or 70 years, up to 2100, what will happen? It is basically called a scenario or projection. We don't call it a prediction. Prediction we call about short-range prediction or medium-range prediction. And climate change is change the scenarios or projections we make. And when you go with a larger time scale, the forecast uncertainty which is given here, or which is mentioned here, also goes up. Uncertainty becomes bigger and bigger when you go for a longer time scale. And this also, weather forecast and climate predictions also depend upon the weather system, the dimension of the weather system. For example, a small dust devil, which is of a very short duration, maybe in few seconds or few minutes, and spatial scales of about few meters. And cumulus clouds is of about 1 kilometer size for time scale of a couple of hours. And severe thunderstorms also is of 10 kilometer, maybe 10-15 kilometer, and also time scale. So right there, x-axis is nothing but meters, the spatial scale, and y-axis is in time scale in seconds. So severe storms comes about 10-15 kilometer in size, but in few hours, maybe maximum to 3 hours. A cold front, which is very popular in US, or here we call it lows and depressions, and that is about 100 to 100,000 kilometer, and highs and lows also of that order. And that we call, that is in few days. For example, the tropical cyclone can form and persist for about 4 to 5 days, sometimes even 7 days. And then monsoon is a very large scale pattern. It's of 10,000 kilometer of scale, spatial scale. These scales are global circulations, a global scale pattern or planetary scale pattern. And then we have water circulation, decadal climate variability, global warming. It's of a very large spatial dimension and also very large time scale. And so when we predict, depending upon the weather system, we have this prediction. For example, severe storm, we'll do a weather forecasting. And the long range, when it comes about monsoon, we say it's a long range forecast because it's a seasonal prediction. So somebody says that I want to give a long range prediction of a severe storm, it is really meaningless. So severe storm is because dimension is very small. So depending upon the dimension, spatial dimension and time dimension is very large, we can have a longer time scale forecast. But it's a short duration weather events like thunderstorms, etc. Our predictability limit comes very small. So we cannot do it in, for example, 1 month in advance. We cannot predict a thunderstorm will occur over, for example, Bangalore. It's not possible. If somebody is predicting, please don't believe it. It's wrong. And so how do we make weather predictions? And weather prediction is a state of art. It's a SND issue, a SND problem. Science and technology is involved. And now we have improved last 50, 60 years. Our weather prediction system has improved, not only in India, everywhere. And in India, the large numerical weather prediction system has improved last 8 to 10 years. We have done substantial improvement in our weather systems, which I will, prediction system, which I will describe in a little later. And what we need as to start with is observations. We need global observation because weather patterns are it's a global, atmospheric circulation is a global circulation. So we need observations not only over India, not only over Indian Ocean. We need observations from Pakistan throughout the globe. So we have all the meteorological services, all countries have an arrangement with through World Meteorological Organization. It is a UN organization like WHO. It's also headquarters is in Geneva. So under that umbrella, we have an agreement with all the countries. We take observation at fixed time. So 0 UTC, UTC means nothing but GMT. That is the morning, early morning, 5:30, then 8:30, 11:30. Every 3 hours we take observation. It's called synoptic observation. Then we also have automatic weather observations, which we can be continuous. It can be every 5 minutes or every 1 minute we can have observations. So, and also we have suite of observations. And once we take these observations, we exchange our observation with all the other countries. For example, our data goes to any other country like US or UK, even it goes to Pakistan or China, and China's data and Pakistan data also come, except for some sensitive data, especially in the border area, and we don't share. But otherwise, all the data we share with the global community, and they all make it because all these countries they need global data, not only regional data. They want global data. And once we talk about data, then it comes a suite of observations, not only from surface observations, observations over land, observation over ocean, observation over snow area, observation over sea ice area, so, and also observation through forest, in the forest, and also observation in the surface and as well as in the atmosphere. So we have different, and also satellites. Satellites make use, we make use of satellite observation very immensely. And I will tell a little later saying that out of 100 data which we use for our weather prediction, 90 data comes from satellites. So that is about 90% of data comes from satellites, and remaining 10% comes from conventional data sets like radio zone, surface observation, Doppler weather radar, ships, data buoys over the oceans, etc. So the first step is having observations, and the observations are taken at different places, very irregular space. And so we need to really first do a quality control, then process it, then we send it to a system called data assimilation. We have to interpolate into regular grids and using some standard method without losing this information of the original data. Then we have numerical weather prediction models. There's nothing but mathematical equations we need to solve. The partial different situations we solve. And this data will be the initial input for solving this equation. And once the model forecasts are generated, whether it's a 3-day forecast, then if you want to produce 3-day forecast, we run up to 3 days. If you want to do a seasonal forecast, we run it up to season. Like that, we do it. And then once your data are available from our numerical weather prediction output, then we do a post-processing. So the real raw data, nobody use it. We need to do a lot of post-processing. And this post-processing data are shared with, for example, India Meteorology Department, and they are forecasted, day-to-day forecast, field forecasters use this model forecast, post-process data as an input, as a guidance. Of course, then they add their own knowledge, their own expertise to finally make a forecast bulletin and give it to public. So that's the way forecast is generated in this country. And before all these things, we need huge computing power, huge computing. So because the mathematical model to be solved in a short time, and we need huge supercomputers. And thank God, thanks to the government, we have plenty of resources for computing now. We have one of the best in the whole world, a 10 petaflop machine we have. And using this computer, we are solving these equations and generating weather forecast. These are the basic mathematical equations we solve in numerical weather prediction, nothing but conservation of momentum, mass, and energy. And these equations are nonlinear, partial nonlinear differential equations. So we don't have an analytical solution, but so that we use numerical method like either finite difference or spectral methods to solve these equations. And if input, then integrate it for further time, future time, and solve these equations and get a solution. So that's what we do. So weather prediction is basically an initial value problem. If you know the initial value, you can predict it for future. And quality of initial data also will determine how the forecast skill is. If the initial value is better, the forecast output will be also better. Of course, forecast skill depends upon many other factors. So initial data, quality of initial data is one of them. And in this equation, if you see that there are terms like F, Q, and SQ, so it's a small term, but it's basically a huge physics, suite of physics involved in it. And so which I will show in the next slide. These are the physical processes which occur in the atmosphere as well as ocean, which we need to really put into the model. And the term Q is nothing but it's a diabatic term, how much heating is generated, diabatic heating is generated in the atmosphere. And that all will be depending upon how clouds form, how cloud condensation process happens, how the clouds precipitate into rain. All these processes are physical processes which we need to put into the model. So we call this a parameterization. So we may not explicitly tell how this physical process happens. One is we may not know some process very surely. So we don't know the things very clearly. So we do a parameterization. We use in terms of pure physics, we talk in terms of some kind of empirical methods. Other way of thing is to save the computational time. If you really parameterize, if you really use explicit physics, we may need huge computing power. To save this computing power, we normally do parameterization. And many of the processes are done in parameterization way. And some schemes, some physical process, we do it a very explicit way. And so for some incoming solar radiation, how it interacts with the atmosphere, like for example, aerosol, clouds scatter solar radiation, but where it absorbs infrared radiation, thermal radiation going from the surface of the earth, then evaporate surface. There are surface processes like latent heat, sensible heat, and clouds. The cloud physics really is a very complex process. So condensation happens, then rain process, etc. Then it comes as rain, and rain also. When it falls, it flows, then river flow, hydrological process happens. So it's a very complex system. All these things which are to be put in a physics way, all these physics are to be put in the model, and we need to really solve these equations. And while integrating the model also, if you take 100 hours for model computations, most of the time, about 60 to 70%, or even little more than that, goes for calculating this physics. The dynamical part, the equation solving and the motions, etc., takes less time, but the physics part takes more time. And so as I told that we have a huge computer. We have two systems, one at Pune, IIT in Pune, and another one Noida. We have center in Noida. We have total put together 8, and we have earlier one or 2 petaflops. So total put together we have a 10 petaflop computing system, which is the best in this country. And 4th best among all weather prediction centers around the world. After USA, UK, and Japan, we are the 4th best computing facility. I'm talking about only weather prediction centers. And of course, people are buying more and more depending upon how much money they have. We also have a plan of upgrading this 10 into 40 petaflops by 2021. And these are some of suite of observations. We have surface observation, left-hand side top figure shows the surface observatories. We get it over land as well as over the ocean. Ocean is, it could be ship observation, it could be data buoys. And then we have radio zone. Radio zone is nothing but we're sending balloons with some kind of temperature, humidity sensor and wind sensors and tracked by radars, and then we can get the particle profile of temperature, humidity, etc. And it's called radio zone instruments. And we have aircraft observation. When aircraft in a flight goes from one place to another place, they take observations and they pass on to weather officers at the particular when they land. And even during flying also, they transmit some of this data. And of course, during this lockdown period because of COVID, this aircraft observation, number of aircraft observations drastically came down. It is obvious because their flights were not there. And right-hand sides are all satellite information. As I said that 90% of observation we use all from satellites, and we have different sets of satellites. One is geostationary platform satellite, is called GeoSat. And LEO is nothing but it's a polar orbiting satellite which will be at a lower altitude. And then also we have a good observation called GPS RO radio occultation technique we use to find out from the bending angle you can calculate the profile of temperature and humidity, which is very powerful data set which we are getting it from satellites. It's a GPS RO. And these are some of the observations, some of the examples of how we take observations. And as I said, vertical profile, when we have so many kind of observations, the question is which observations are more useful, where we have to invest more. So we have done, many people have done this exercise to see the sensitivity of these observations for improving the weather forecast, our skill of weather forecast. We also did the exercise a couple of years back. Then we found the vertical profile of humidity and temperature is very, very crucial. And if we can get more vertical profiles, we will get much more better forecast. So we over the land we can have so many observations. We can send balloons, and we can have, for example, wind profilers to get winds, and the microwave radiometer we can get vertical profile of temperature, humidity. But over the oceans we don't have much resources. So we are our community was talking about the vertical profiles of temperature and humidity, and also wind. And from satellites. So, of course, satellites provide vertical profile of wind, temperature, and humidity even earlier. But wind profiles were not available. So, recently, European Space Agency has come out with a satellite and the satellite platform called ALUSE, first space-based Doppler wind lidar mission. It's a very ambitious program. We are all waiting for this data to come. And I'm happy to see this data. Even we started getting this data from European Space Agency. We started assimilating in our model, and we find that huge impact in ALUSE data, vertical profile of wind from the satellites. So this is one example how really the satellite technology can really help weather forecasters in improving the forecast. So now people are talking about what could be the new kind of observations which we need. For WMO is really now discussing about. Now WMO is discussing, World Meteorological Organization is discussing. They don't now discuss about atmospheric observations or ocean observations or observations for cryosphere, observations for land process, etc. Now they talk about Earth system science. But it's an interactive process, and the whole Earth system science is nothing but atmosphere, ocean, cryosphere, everything, biosphere, everything put together. So we cannot talk about observation only for atmosphere. We cannot talk about observation only for ocean. So the concept called integrated Earth observing system. So that is the new concept, and in which of course we are talking about many components. Recently, a document has been prepared for WMO, and so there are very innovative ideas are coming up. What kind of observation? For example, crowdsourcing from ground-based traffic. When people travel, we can have a mobile app, and they can get the observations, and they can pass on to you. It will be very unconventional. It may not be at the fixed time, but observations are very useful. And so crowdsourcing is one solution, one possibility, one solution. And another is we are talking about CubeSats. It's a small satellite of maybe 4-5 kilogram in weight, and small satellites. You can launch in one launch. We can have so many CubeSats. And so that CubeSat is a new concept in which we can have observation. You can even put microwave sensors there. And of course, precipitation from mobile towers. We have plenty of mobile towers. Mobile users are going up, especially in India. So we can derive precipitation from mobile towers. That's a new technology which people are talking. And we are also started doing some work. And low-cost sensor, air pollution, for example. We don't need very highly sophisticated air pollution instruments to measure air pollution. We can have a low-cost sensor. Of course, it's all depending upon what is the quality of the instruments. We should not forgo the quality. We should not compromise for the quality of any observations. And the vertical profile from lower part of the atmosphere is very crucial. And for example, when you send the balloon up, it goes very quickly. 1 kilometer, it goes in a few seconds. So what will happen means in first 1 kilometer, we don't get much observations. So we need a special kind of observations to get only the vertical profile in the lower atmosphere. Then we can use of unmanned vehicles, UAVs, and Internet of Things. These are the things which we now talk. And the modeling framework is the next is models. As I said, we solve mathematical equations. And before that, before discussing the how we solve it, etc., this is a good, beautiful discovery made by Edward Lawrence. He was a professor at MIT in the early 60s. I was born in 61, so 61 this paper came. And this paper clearly shows he tried to solve this equation which is shown here. And he said that the results, the solutions of this equation really heavily depend on the initial data which he started using. Instead of 76.8, if you use 76.853, the solutions are different. So what he said, finally, he said that the atmosphere has a finite limit of predictability. If you change the initial condition, even a small change, it can give a different solution. So, and he termed it butterfly effect, or theory of chaos, and etc., which for many of us we know about it. So there is a limit of predictability in the weather prediction. So that is the fundamental thing which we need to really keep it in mind. So if you really talk of all times the forecast in different time scales, this is the way the forecast skill goes. You can see the left-hand side is the weather forecast. It starts from first day, of course, the weather forecast will be good for today. And then it tapers very quickly. And beyond 10 days, the forecast skill is very poor. And in extratropics, this is called the limit of predictability. So in extratropics, it could be 8 to 10 days. In over tropics or India, it's 5 to 6 days time. The predictability limit is. So the forecast skill goes sharply down when we go for a longer time scale. Then in between there we have some skill comes from extended range forecast, we call S2S predictions, and that was not well tapered, we researched in the earlier days, but now we do a lot of research on these S2S predictions, and we have a prediction system for extended range forecast. Then seasonal forecast, we have been doing it for more than 100 years, and there is a skill there, and also there is a skill in climate projection. So but these are all below the weather prediction skill. So that we should understand. So these are the different forecast ranges and also the skill, how it goes. And the mission mode, so we have started the mission mode program and a few years back, 2012, to improve the quality of forecast. So what we could do is we could achieve all these forecasts, the development of all these forecast models through this monsoon mission. And this is the suite of models which we have. We have starting from a 400 meter Delhi air pollution prediction model. And we have a Delhi fog model for Delhi, and we have 1.5 kilometer regional model. We have global model of 12 kilometer, and also we have a system model of 150 kilometer, which will be used for climate change prediction, and coupled model about 32 kilometer model we have. And this is the way the forecast skill goes. You can start from 1999 to 2020. This is root mean square of wind at 850 at 1.5 kilometer. If you really calculate over the Indian region, what could be the root mean square? You can see that the error is coming down. It started from 6.5 to now it's almost less than 4.5. So this is all depending upon, of course, many factors. One is we move to a higher resolution model, and also physics has changed. And most important thing is we started assimilating more and more data, good data. So that has really resulted in improvement in weather forecast. And this is another forecast, slide which clearly shows the skill of 3-day forecast a few years back. Now, 5-day forecast, now we can do it in 3 days. Sorry, the other way. The 3-day forecast scale, now we can even go up to 5 days scale. And what we could do it in 3-day scale, now we can even go up to 5-day in advance. So 2 days advantage we got it by moving to a model of 12 kilometer, but much improved physics. And some of application I can show is Gramin Krishi Mausam Seva. This is basically for farmers. We reach to almost 42 million farmers now, almost twice in a week, in a week, and we provide them agrometeorological advisories. And another is, of course, we all know the tropical cyclone forecast skill, which is one of the best in the world now we are. And this is the Umpan, right-hand side shows the track and actual and predicted for cyclone Umpan. And now the error for landfall error is almost 10 to 30 kilometers up to 2 days in advance. It's pretty good. So we are able to tell the landfall of the prediction, tropical cyclone well in advance. And this is the thing which I mentioned in the beginning is the forecast for wind and the energy sector, which is coming up in, largely by private industry. So they want forecast for next few days and a couple of days before. And also they want a very high time resolution. For example, every 15 minutes they want forecast for wind, solar as solar energy. And we have started doing a lot of experiments, and now we are catering to many industries now. And these people are happy with the forecast, and there is a good skill, wind forecast. It's a challenging job because we have to forecast every 15 minutes what will be the wind strength at 100 meters. That's where the windmill is established. And also solar energy. Solar energy in clear skies are pretty good. Forecasts are pretty good. But when it comes the cloudy region, when the clouds comes, then the forecast is not that good. And this is the verification which people have done, Gangobadi et al. In Current Science in 2019. And ensemble forecast is nothing but, as I told that forecasts are very sensitive. Forecasts are very sensitive to the initial conditions. So if we want to go for beyond time from 3 days or 4 days or 5 days, there is a concept called ensemble forecast. You perturb the initial conditions and generate more and more forecasts. Then you do a kind of a probabilistic forecast. Instead of deterministic, instead of saying that 15 millimeter rain will come over particular area, you can say what is the probability of getting 15 millimeter over that area. So you convert into a probabilistic. For probability calculation, you need many samples to calculate. And so we started the ensemble forecasting system, which is one of the best in the world now, a 12 kilometer global model with ensemble. We have 23 ensemble members because of computing resources, limit of computing resources. And these are we found that these are very, very useful. And when compared to deterministic model, and especially predicting of extreme weather, very heavy rains and or extreme winds, ensemble forecasts are very, very useful. The right-hand side, you can see that there's the map we have generated, probability of rainfall more than 66 centimeters per day. What could be the probability? This will give a good guidance for the people who can take action on that. And this is a new guidance which we provide to the people is extreme weather guidance. This is also based on 95th percentile or 90th percentile. And this percentile we calculate from the hindcast of the model, not from the observation. From the model, we calculate the percentage and we generate this extreme weather guidance for extreme rain, heavy rain, extreme windy conditions. It's also, we found that very useful. And this is a heat wave forecast. Instead of saying that temperature will be 42 or 43, we can tell what is the probability of temperature exceeding 40 degrees. And where we can expect this kind of this high temperature of exceeding 40 degrees. And this is a good example of Kerala heavy rains in 2018. Maybe there's a lot of floods. So we try to do kind of analysis, past analysis, whether we can, instead of quantitative number, could we generate some kind of probabilistic forecast and see whether we are able to predict that heavy rain. So we could find that up to 2 standard deviations, some skill in predicting the probability of a heavy rain which occurred in August 2015. A new initiative is one is a flood warning system which we introduced for Mumbai. And as you know that Mumbai also is every monsoon season they get flood, and so this is a very state-of-the-art flood warning system which we introduced and inaugurated this year with the help from Mumbai Municipal Corporation. It was developed by scientists in NCCR in Chennai. And this year on 5th August they had very heavy floods which the flood warning system could really pick up, and they could also say that which region the water level will go up and down. So, and depending upon our guidance, they could really put the people on the job for removing water. For example, they could locate the water pumps to pump the water out, etc. So that kind of a very useful things they could do it. So we already learned a few years back for Chennai. This is the second time that we are doing it for Mumbai, and we'll be doing next time. We'll be doing it for Calcutta. And so to generate this forecast, we need original data. We need initial data, huge data, rainfall data. We have already set up about 170 rain gauges, very high quality rain gauges. And we are now putting about 3 radars there. And if you put the radar, 3 radars plus this ground station, ground ARGs, we can generate rainfall at every 500 meters. That's what we are expecting, at every 15 minutes or so. So that will be very accurate observation, very high resolution observation, both in time as well as space, which people can really use it. And we will develop a mobile app so that they can see at the given time where it is raining more, where it is raining less, etc. The radars have, we have placed the order for radar because of COVID, it is delayed, but I am very sure that before the next monsoon, we will be installing these 3 radars there. And another thing is the fog, winter fog, as all of us know that Delhi airport, if you really want to come to Delhi, somebody wants to come in winter, they will always have uncertainty of fog and flights will be diverted. So we have done a lot of experiments for the last 3-4 years, and we could develop a winter fog prediction for Delhi airports, and which is doing reasonably well. Not up to the mark, but reasonably well, which is very useful, and airport authorities are using it. And of course, we do a lot of research also to find out, for example, fog layer, to predict a fog layer. What are the important ingredients? One we find is the data assimilation from the land surface, especially what is the type of land surface and etc. So if you really start doing land data in assimilation in the model, we could really improve our forecast for fog. That's what we found, and the papers are being published on these results. And another thing is the air pollution, the quantity of air pollution over Delhi. That also we have developed last year. Now we have a 400-meter resolution air quality forecast model for Delhi, which is really doing well. And this model has the capability of assimilating chemical data, and so which we do with in collaboration with NGAR. And we have done extremely well. And we have also developed a new forecasting system, similar system, with the help from Finnish Meteorological Office, that also of very high resolution forecasts are being generated for air quality. And we did, this is the good results from COVID. During COVID period, left-hand side shows that how the people driving and walking have stopped. That is data taken from Google. And the right-hand side shows the reds are 400-meter model forecast and blacks are the observations. You can see that before lockdown, the forecasts are pretty good. But during lockdown, when no correction to emissions when we did, the model predictions are much more. But when we try to predict, make the corrections in the emissions, as we all of us know that during lockdown, most of the emissions were not there because most of the air transport sector is down, industries are down. When we really introduce that changes in the emission, we could really predict the very low level of air pollution level over Delhi. So this is very important result which we are want to inform. Extended range forecast is nothing but forecast for 15 to 30-day time scale, and there are different aspects, different sectors. We can use it for agriculture, water, energy, disaster, human health. And this is one example how these forecasts are generated, how the skill is of monsoon rainfall and extended time scale. For example, we have weak monsoon, active monsoon. So we have the models are pretty good. The extended forecast system is pretty good to at least to have a prediction of at least 2 weeks before whether it will go from weak monsoon to active monsoon, from active monsoon to weak monsoon. So that transitions are well predicted by the system at least 2 weeks before. And this is the example how we predict extended time scale for CIs and ocean parameters, Arctic CIs and the ocean parameters. And these are new results which have come out from our group scientists from IITM Pune. They are now using extended forecast for application in health sector, especially for malaria. This is a good example how this model extended forecast system can be used to predict the possibility of getting malaria over a specific region, at least in 2 weeks time scale. And seasonal forecast is pretty known as very popular. And as all of us know, the monsoon rainfall, our agriculture production in this country depends on monsoon rainfall. This is a very famous result of Gardle and Gardle 2006, which shows that monsoon rainfall, the impact on food grain production in this country completely depends on monsoon rainfall anomaly. It's a large negative anomaly can bring down the food grain production very substantially. And of course, this relationship is not really a linear. It is little non-linear. Right hand side, you can see it's a little gets plateaued. And but the answer is the message is that food grain production is completely depends on monsoon rain. So we try to predict it on seasonal time scales. So traditionally, IMD has been using statistical models. Now we also have a dynamical prediction system which IATM has developed at 8 kilometer, and also recently Ensemble has developed another climate prediction system for seasonal forecast. But we have problems. So for example, this is a figure shows what are the precipitation bias in the seasonal forecast model, which clearly shows over central India there is a large dry bias. The model predicts much less rainfall than what we observe. And also there is excess rainfall over Pacific and etc. So there are a lot of model bias. And also when compared to the skill of other models, this model is comparatively far better than many other dynamical models, the model which we developed under the monsoon mission efforts. And this model is one of the best in the world now. And of course, still is close to 0.6, about 35% or 36% of monsoon rainfall is predicted by this model. And but there, as I said, there are a lot of model issues. For example, this is a correlation of monsoon rainfall with SST, and which clearly shows this model is predicting more dependence on sea surface temperature over Pacific. The correlations with the Pacific temperature is much more than what we see in the observations. So when El Nino comes, the model will predict a very large drought. When La Nina comes, the model will predict a large scale excess flood monsoon season. So its dependence on El Nino and the ENSO conditions is very large in this model. And however, the Indian Ocean relationship is not well predicted in the model. For example, sea surface temperature over East Indian Ocean is very much related to monsoon rainfall. When sea surface temperature goes up, we get less monsoon. But however, this model, the monsoon prediction model, it is not the same story. It doesn't show the correct signal. And climate change projections, we also have a S-system model developed by our group in IATM. It's the first time we developed a S-system model, which we use it for climate change projections. And okay, so we using this model, we have now making a lot of projections for climate change assessment. And so we have brought out a beautiful climate change assessment report, assessment of climate change over the Indian region, edited by Krishna. The book is freely available. Anybody can download this book. Also the data are available at IATM, which we can use it. And also one or two more slides I can show is that one is that we also do a lot of intensive campaigns, observational campaigns to understand the physics of atmosphere, especially clouds. We have started a campaign in CAPEX. And this time what we did is for last 2 years, we made a campaign for understanding the cloud seeding process, artificial rainmaking process. All of us know that, especially in Karnataka, immediately when a drought comes, immediately they go for cloud seeding. So we did a 230 hours of observations, probably the first time by any country, large scale observations we have taken. Now we are bringing out a white paper on how the cloud seeding is to be done and what is the commercial viability of the cloud seeding. And also we are setting up a new atmospheric research testbed in Bhopal, which is also one of the best, it could be one of the best in the world now. It's a state-of-the-art observatory we are setting up. And future plans is we are going to improve our observations, improve our data assimilation. We are improving computing facility from 10 petaflops to 40. And we are trying to have a new dynamical 4 NWP models, which is going very well now. And of course, we are talking about our S-system modeling, not only atmospheric modeling, ocean modeling, separately seamless prediction we are talking about. And coupled data assimilation is the new area where we are working. And we are going to bring a high resolution model. By next year, we will have a 5-kilometer global model. And also we'll have 1-kilometer urban forecast model. And we'll have more members for Ensemble Forecast, scale our physical parameterization we'll do. An application of artificial intelligence and machine language is another way of doing improving our weather forecast, as well as especially on data processing. And also you can even use AI and ML techniques for even replacing parameterization methods, which we use in model processing, cloud physics, radiation, etc. So these are the new areas where we are going to work. And I will show these are maybe one of the last slides. Is people are even started developing running models for 1-kilometer resolution with explicit convection. No parameterization of clouds, how it forms and all, but explicit convection at 1 kilometer global model is a new result that's come. It's very, very interesting results which have come out, which have become very popular. Vedi et al. In 2020. You can show the bottom two slides, bottom two figures. You can see the left-hand side is the model forecast of 1.4 kilometer. Right-hand shows the satellite observation. This is a very, very beautiful resemblance of global model forecast at 1 kilometer and observations. So this is a new area which we are trying to, now all of us are looking for very high resolution global models with explicit convection, etc. So this is the conclusion. So MIOS has one of the best weather and climate prediction modeling framework, thanks to efforts to our scientists, as well as fruitful collaboration we have both from India as well as from abroad. And MOS provides service to various users starting from nowcasting to climate change prediction, so many decades in advance. And also we are engaged in active research to further improve the skill and fidelity of these models in collaboration with researchers in India as well as abroad. Of course, our outreach, the communication strategies, also we are improving. When you compare 2 years back, outreach was not so good, but now we are improving our presence in social media is too good. And we are improving our outreach also. With this, I will stop. Once again, thank you very much for giving an opportunity to give this special talk on climate and weather and climate prediction over India. Thank you very much. Thank you.